In lecture 39, we will cover 2-3, which essentially is 2-3-3, except that there are no independent new axes. The extra threefold axis is not independent, and so instead of being 2-3-3, we can do our usual thing here to show that it'll be called 2-3, and that's because, of course, with threefold axis, if we let the axes pass through in 3 dimensions, then you'll see that with the other twofold, we don't need the extra threefold axis. Or another way to look at it is the motifs are identical around all the threefold axes. So this is the first example where we have not the n22. Remember, all of our other cases were n22, and we had finished those. Again, we could have had you with our cosine A, cosine B, cosine C equations gone through and with a computer program or by hand looked for all potential solutions. Of course, we kind of told you ahead of time that the 1-1 series, where you have no other rotations, just the main axis, is going to be our first 6 solutions. And then we told you that most of the other ones are in the form of n22. But now there are 2 cases where they're not along this diagonal, if you will, because remember these solutions were along the diagonal where A and B were 2-2, and then C is some other number. And then now here we have a 2-3-3 as one of the solutions. Well, I guess this is actually, if you were to pick A and B being these 2, then it's still along the diagonal, and we have n equals to 2. And so this is another one of those solutions that would work if we were to put in to alpha 100 and gamma here 180 degrees, and then I put into beta 120 degrees, and then alpha 120 degrees. It turns out that those solutions do converge for cosine A, cosine B, cosine C expression where we had inserted the 180 minus gamma, etc., and transformed the the law of cosines for a spherical triangle. And in this particular case, if you insert those angles of rotations around the axes A, B, and C, you end up with A equals B equals 55 degrees. And you guys should recognize that if you're at all familiar with Miller indices and single crystals, because this is a classic for cubic materials. This is a classic case of the angle between a 1-1-1 plane and an 0-0-1 surface. So this is actually shows up quite a bit, because if you take a cubic material and let's call this surface, the 0-0-1 plane, right? So this is maybe even call that one directly the 0-0-1, let's say. Then if I look at a plane coming out of here, and this is, x, and this is y, then a normal coming out of this plane, if I draw this down here, is the 1-1-1 direction. And if you dot this to get the angle theta here, the angle between this normal and 0-1 is the angle between this plane and the normal, and that turns out to be 55 degrees. So you'll recognize then that this is a typical angle between 1-1-1 planes, and of course, since A and B are the angle, A is the angle between axes A and C, and B is the angle between A and C. You can see that we're going to end up using the cube as our positioning, where we say let's have the C axis come out, and we'll make that the 180 rotation, and that the angles between, therefore, this threefold axis and the normal, and this threefold axis and normal is 55 degrees. And that makes sense because, of course, this is coming out of the diagonal, which means that it's attached. It's the normal, for example, to this 1, 1 plane there, and this one is normal to the 1, 1 plane coming out of here, right? So it makes perfect sense that the line coming out of the normal face of a cube, we already know that the angle between these guys is going to be 55 degrees, and indeed, what all the cosine A, cosine B, cosine C is telling us is that these threefold axes with respect to C are going to be 55 degrees. And of course, using the cube as this and saying, all right, this one must be coming straight out, this one's coming out of the diagonal of the cube, it won't be a shock either to see that, of course, the angle between A and B, which would be C, is 70.53 degrees, and that's typical of the angle between 1, 1 planes. And of course, you know, the way we've done it here, B is perpendicular, is the normal to, you know, this 1, 1 plane, and this one is normal to this. So that means that the angle between the two is the angle between the planes. And if you were to take these two 1, 1 planes and do the G1 dot G2 vectors, you'd find out that theta would be 70.53 degrees, which is the angle between 1, 1 planes. So again, this 2, 3, 3 ends up being, no matter how you slice it, connected to the cube here. And we're showing you the stereographic projection here, which, of course, Bernie Vench, the originator of this class in material science and engineering, used to always make the joke that you know, this is of course a jack-o'-lantern. So for this class has been in the fall for years, and so the 2, 3 is the is the jack-o'-lantern stereographic projection, because you know you can see here that it might look like if you inserted one extra not asymmetric threefold axis, you'd end up with a nice smiley jack-o'-lantern. But of course, that is not the case. But it is October here in the fall in America, so that is a little joke. All right, so the stereographic projection, of course, is just trying to show that these threefold axes are coming out of this center, right? They're coming out of these diagonals, right? Remember, this is a sphere. This is supposed to be representing a sphere, and that this C pi here is coming straight out the top, and then we get ones coming out there, out the bottom, and one out the back, which is, you know, this one here, but you just can't see it. And don't forget that these guys extend, of course, up behind here, and the axes pop out on the other body diagonal. So see here, this goes down, and then it goes out the other body diagonal. This one here comes out and ends up coming out here. And that's why you end up without the unique axes, because if I take this one going out through here, and I take this one going out through there, and then I rotate it by 180 degrees, then the other guys, the one coming out of here, the one going out of there, show up, and I end up with all of my axes. So again, just like we did in 2D, where the fact that, you know, when I had the threefold itself, you know, with the 120, but if for whatever reason, because of mirror planes or whatever, I let this guy extend, and in our case we have to because we're in 3D, so the three-fold axis does not just end in space, it is an axis that travels through, right? And so you automatically generate the guys on the other side, and therefore there's no unique, like we were looking at mirror planes and things like that, if I lined them up along there, there'd be no unique generation. And here it's the same thing. The threefold axis I'm showing coming out and up here, you know, has to travel through and come out this back side. And so with the pi rotation, I end up not having any unique threefold axes, which means I can drop, you know, just one type of threefold axis, which means I can drop that. And of course, you know, the motif way of looking at it is if I had any motif around here and around here, it would also show up equivalently on the other side of this box coming out, because remember I have the threefold axis popping out the other side. And then when I rotate, I get the same exact thing here, over here, and over here, because it's just a 180 degree rotation. So hopefully that explains 2-3 to you. Just one last thing, I'll clear up the situation here a little bit so I can go back, and wanted to show you that remember when we're looking down at a threefold axis in the corner of a cube, remember what you're kind of seeing. The cube top moves away from you like that, and so that's the top face of the cube, right? And then you've got the edge that's coming down here, and this is the side, and this is side, so you can see more easily the threefold here. I think one way to see that the motif works in this case is, if I pick this guy, and I admit this one's a little bit confusing, but if I'm looking down here and I rotate to the right 128 degrees, this thing comes up and over and actually lands on this other, point here when I go around 120 degrees. And then of course, if I look at the rotation around B, this axis, this doesn't move position at all. And then this guy is related by a rotation around 180 degrees. So that's one way to see. It's a little bit tricky on this one because the cube and the neighboring cubes, you have to make sure that you're rotating through the same points, and it's a little tough. But if you choose that one, that is start here, I think you can see that if you rotate about this one and you end up on the other corner, and then when I look down at the b 2 pi over 3 here, just in this particular case, it doesn't move because I'm passing right through that corner. And then it rotates back with this pi over 2, or goes this way with the, c pi. So that is 2, 3.